From the relationships we described in our last video, you might guess that the rate of reaction is related to the concentration of the reactant. I know we showed both the reactant and the product in that video, but at the very initial state, remember that the concentration of the product is 0, and it's always going to be 0, so that's not as useful as thinking about it from the reactant side. But how does the concentration of the reactants affect the reaction rate precisely? This is why we theorize using mathematical models. They help us think concretely about the relationships. But before we even start to build a model, we have to have some idea of what we want to describe. So first, imagine that we have two reactants, A and B, dissolved in a very low concentration solution. You might even close your eyes and imagine yourself as one of a very small group of A's searching through a huge crowd to find one of your friends, B. Because there are so few of them and so few of you, it will take time to find each other. We could describe this by saying that the rate of A plus B turning into AB is slow if the concentration of A and the concentration of B are low. Now imagine if we had the same size crowd overall, but it contained a lot more A's and B's. Now you would have a much easier time finding a B. In other words, the rate of A plus B into AB is faster if the concentration of A and the concentration of B are higher. This intuition can be translated into a mathematical formula by saying that the rate is directly proportional to the concentration of reactants A and B. We turn this into an equation by adding a proportionality constant, which we'll call K. This is a good place to start. It captures what we would expect to see in terms of rates of reaction and concentration of reactants. But then we did as scientists do, and we tested against experiment. The world or the universe being the only reliable measure that we have to test what we think against what we can actually see and observe. What scientists found was that reaction rates don't depend on the concentrations of every reactant equally. Some reactions depend on only one concentration or the other. Some depend on one concentration twice or the square of that concentration. And others don't depend on concentration at all. So instead of throwing the theory out completely, what we can do is extend the theory to contain the new information. In this case, we do it by adding exponents to each concentration. Now it's important to remember that we can't know the value of the exponents x and y beforehand. Those are determined by experiment. They are not the stoichiometric values of those reactants. The sum of the exponents also turns out to be a really useful piece of information. That's what we call the order of the reaction. The orders we look at in this course are either 0, where rate just equals K, that's the 0th order, rate equals K times the concentration of one reactant, or first order, and rate equals either the concentration of A squared or the concentration of A and the concentration of B, both of which are second order reactions. Forming the rate law of a reaction is a good example of how theoretical and experimental methods can work together to give us important information about the natural world that neither one of those methods could give us alone.